So dear students, today we are continuing the topic center of mass. As we have already discussed about the center of mass of a system having two mass particle or three mass particle arranged in a plane or along a straight line. Now at this time we will consider a system of n number of particles where its mass particle can be situated in any of the three-dimension place. In that case, what will be the value of position of center of mass from the point origin? Let's see. Center of mass for a system having n number of particles arranged in space such that the position coordinate of all mass particles corresponds to an orthogonal coordinate system where the three different axes are there: x-axis, y-axis, and z-axis in three dimension, in three directions. So for that system of particles, we have to calculate the position of center of mass for the system. As we have seen earlier, we can say the position coordinate of its center of mass along the x-axis will be x equals to m1x1 plus m2x2 plus up to mnxn divided by m1 plus m2 plus up to term mn, which can be rewritten as sigma mi xi divided by complete mass of the system. Similarly, the position coordinate along the y-axis or z-axis for each mass particle y equals to sigma mi yi divided by capital M, and z equals to sigma mi zi divided by capital M. The all three positions along the x, y, and z axis for the center of mass of the system can be combined to express the position coordinate of its center of mass, where the center of mass will be at some distance from the origin and can be expressed by its position vector from the origin. So let's say capital R is the position vector of center of mass of the system from the origin. So if the position vector of center of mass of the system is capital R, then the capital R vector can be expressed in terms of all the positions of each mass particle along the x, y, and z axis. Means the value of position vector for the center of mass R can be expressed as x I cap plus y j cap plus z k cap, where I cap, j cap, and k cap shows the unit vector along the x, y, and z axis direction in the orthogonal system, and x, y, and z is the magnitude for the position of the mass particle in that space along each axis. So x express its position along the x-axis, its coordinates, and y express the coordinate value along the y-axis, and z express the coordinate value of center of mass along the z-axis. And in the combined form, its position in that orthogonal system, the position of mass particle, all mass particle in combined form, or you can say the position of center of mass of the system can be expressed in the combined form of all the position along all axes, and which is expressed as r vector. Similarly, if we say that we have to represent a position vector corresponding to coordinates of position for each mass particle, then for each mass particle we can give another vector, say small r, for expressing position vector of position of a mass particle. Definitely, the position vector is with respect to the origin for the system as well as for the mass particle. In that case, say the position vector is expressed as small r I that correspond to the specific number of mass particle number 1, 2, 3, and 4, or so on, which can be given as xi I cap plus yi j cap plus zi k cap. And finally, we can show the relation between position vector of center of mass and position vector of mass particles from their origin. So in that manner, the relation between the position vector of center of mass and the position vector of mass particles small r can be given as r vector equals to sigma of mi ri vectorially divided by the complete mass of the system, capital M. The sum here we are expressing here, summation of mi ri, is the vector sum of the term mi ri for all mass particles. So if the origin for the center of mass is chosen, then definitely the term sigma mi ri will be 0, because if the center of mass of a system lie at the origin, then the position vector value will be 0 for the center of mass, and in that case the term sigma mi ri will be 0. So we can say here, if the center of mass of the system lie at origin, then sigma mi ri will be equals to 0, because the vector sum of all position vectors of the mass particles will represent the position of center of mass at origin, and the coordinates of origin are 0, 0, 0 along all the three axes x, y, and z. Let us take an example to find out the center of mass of a system. Find the center of mass of three particles at the at the vertices of a triangle. The triangle is equilateral triangle. The masses of the particles are 100 gram, 150 gram, 150 gram and 200 gram respectively. Each side of equilateral triangle. Each side of equilateral triangle is 0.5 meter long. Let us first draw an equilateral triangle showing the system of mass particles at its vertices. The mass particle are there. So this is the solution. See, the triangle is such that its one of the vertices lie at the origin. The coordinates are 0, 0 for 100 gram mass, and coordinates for 150 gram mass are 0.5 and 0, and coordinates for 200 gram mass 0.25, 0.25 root 3. See here, the situation is such that here the coordinates of point B you can calculate by drawing a perpendicular from B on x-axis, where the position of perpendicular crossing on x-axis is at 0.25 coordinate and the height of the triangle is 0.25 root 3. Now see, in this case the x coordinate of the mass particle we have to calculate the 200 gram mass here at point B. X coordinate of center of mass can be calculated as x equals to 100 multiply 0 plus 150 multiply 0.5 plus 200 multiply 0.25 divided by the sum of the masses 100 plus 150 plus 200. So this will give us the value 125 upon 250 meter equals to 5 upon 18 meter. Similarly, the y coordinate for the center of mass y coordinate of center of mass will be y equals to 100 multiply 0 plus 150 multiply 0 plus 200 multiply 0.25 root 3 divided by the total mass, which we have already calculated in the x-axis coordinate, the 250 kilogram, 250 gram. So here the value of y gives us